All right, hello and welcome to our second class of the semester. Um, Here I'm actually setting my phone on Do Not Disturb. There we go. Second class of the semester, but this is our first lecture. Lecture proper. We're starting today with chapter 1, which is the place that you want to be starting. So we're going to just go ahead and dive in. If something's not making sense, totally drop a question in the chat, and as always, this will be available afterwards on the channel. So let's go ahead and start. So chemistry is, if you were to look this up in the textbook, look it up, ask for a generic answer. Chemistry, and our textbook would tell you this, is the study of matter, right? That's the definition that you find in the book. It's a satisfactory answer, but really, if you I'm gonna relocate my lecture notes. So it's a fine answer. Like I said, it's not wrong, but though it's satisfactory, it's lacking something. It's a little stale, and it's slightly off the mark. If you just put this question to anybody, say fill in the blank, chemical blank, and what's the first thing that comes to your mind? The first thing that comes to mind is reactions, right? Chemical reactions, and chemical reactions, transformation. Chemical reactions are processes that transform chemical structures, that take reactants and turn them into products. All right, so in a lot of ways, I think it's more accurate. It might be a better description for chemistry to describe it as the study of changes in matter rather than the study of just matter as is. Now, matter is definitely a part of it, but what this field is known for, and kind of where it's made its mark, is through reactions, through changes. How does matter change? What types of things accompany the changes in matter? What kind of energetic differences exist between reactants and products, etc. So anyways, just that's kind of the big picture. We're going to be looking at matter, yes, but with an emphasis on how it changes, why it changes, etc. So matter, however, is where we're going to start. Matter is one of two fundamental quantities in the universe. The other is energy, and matter and energy make up everything in the universe. All right, that is everything. That encompasses everything. When we talk about what matter is anything that takes up space so it has some sort of volume, right, that it occupies. It takes up space and has mass. If something both takes up space and has mass, has a weight to it, it is categorized as matter. And matter comes in 3 different flavors. All right, there are 3 different flavors or phases of matter, and those are solids, liquids, and gases. All right, the solid phase, the liquid phase, and the gas phase. And we have, I feel like we have an intuitive kind of sense for these three phases because we've interacted with them, right? We're breathing a gas. We drink liquids on the regs. We are solid. Actually, part of this is liquid too. We interact. We eat solids primarily, right? So we all have some sort of intuitive sense for what these three phases of matter, how they behave, what they are, etc. But just to like kind of put it down formally, excuse me, we can talk about each phase with respect to its shape, the shape each phase has, and the volume or space that it occupies. And if we're talking about shape, we say that solids have a definite shape, right? There is the shape that a solid has, and I've already made my first spelling error. Not surprising. Solids have a definite shape. The shape doesn't change, right? A rock is a rock, and it doesn't morph into something else unless it gets melted into lava, right? Molten rock, and then it's in a different phase, right? So solids have a definite shape. Liquids have an indefinite shape. Oops. All right. Liquids don't have a definite shape. They flow. They take the shape of whatever container is holding them. Gases also have an indefinite shape. All right, and then that makes sense, right? We're breathing gases. Gases occupy the volume of whatever is holding them. Now, so those are the shapes generically of each phase of matter. We can also talk about the volume. Now, the volume occupied by a solid is definite, right? It doesn't change. And the volume occupied by a liquid is also definite. All right, if you have 2 liters of soda, it doesn't matter if you take the 2 liters of soda and pour it out into a bowl. I don't know why you do that, but if you did, it would still occupy 2 liters in a different shape, right? Because the shape of a liquid is indefinite, but the volume doesn't change. The volume of a liquid is defined. Now, gases are weird because in addition to having an indefinite shape, gases also have an indefinite volume. A gas will actually stretch or compress to fit whatever volume you're storing it in. So gases, indefinite volume, indefinite shape, they're the loosest, right? Solids, definite shape, definite volume. They're like the most rigid of all phases of matter. And then liquids are kind of in between, right? They have an indefinite shape, so they're flowy, but they have a definite volume. That doesn't change. And here you see, so liquid is kind of like the intermediate or in between. It shares some properties in common with solids, and some properties they share in common with gases, right? And now, we're like 10 minutes into our first lecture, and we've already covered 3 of the 4 bending nations, right? We have Earth Nation with solid, water tribes with liquid, and then the airbending nomads with the gases. And where's fire? Where's the Fire Nation, you may ask? Fire's energy, not matter. So that'll come later this semester. We'll get there eventually. All right. So that's kind of like an introduction to the phases, the forms that matter can take. But let's talk about a little bit about the changes matter can undergo. All right. Let's talk a little bit about how matter changes. Now, matter can undergo 2 types of change. All right, there are two types of change that matter can undergo. So let's talk about changes in matter. We can always skip the Fire Nation. Don't tell Lord Ozai. All right, let's talk about changes in matter. There are two fundamentally different ways that matter can change. And the first is known as physical change. The second is known as chemical change. All right, now when we talk about physical change is any change that does not alter the chemical structure of matter. So a great example of physical change would be cutting my hair, for example. Cutting my hair is a physical change because, whoa, that was unexpected. There we go. That's what I wanted to do. Cutting my hair is a great example of physical change because before and after the haircut, my hair on a fundamental molecular level is still hair, right? So a haircut is a physical change. It's hair before, it's hair after. The only thing that's changed is the hair is no longer physically attached to my head, right? But I haven't fundamentally altered the structure of the molecules. They're hair before and after. Now, chemical change is different. All right, chemical change is change that alters the chemical structure of matter. All right, that is the definition of chemical change. And chemical change, so an example of chemical change would be well, like lighting my hair on fire. Right? If I were to, instead of getting a haircut, which would be a physical change, if I were to burn all my hair off, that's an example of a chemical change because there isn't hair anymore. There's not hair. With a haircut, your hair gets disconnected. When you light your hair on fire and it's done burning, you put the fire out, you don't have hair. The hair reacted through a chemical change, through a chemical process, to become carbon dioxide and water, vaporized into the atmosphere. All right, that is an example of a chemical change. In general, physical change is reversible. Now you may be thinking like, wait a minute, a haircut's not reversible. Yeah, technically, if you were super bored, you could take every piece of hair and like glue it back onto your head. You could reverse it. Chemical change in general is irreversible. You can't, once you've burned off all your hair, you can't unburn it, right? You can't grab all the carbon dioxide and water from the atmosphere and reassemble it into a gorgeous head of hair. Not possible. So Chemical change tends to be irreversible. Physical change tends to be reversible. You can do it, then undo it. But the fundamental definition is a physical change does not alter the structure on a molecular level, but a chemical change does. All right, and those are the two ways that matter changes. And we'll take time studying each of these throughout the course of this semester. All right, now, before we get to kind of some brass tacks, kind of we're going to get into some math, right? We're going to get into units and measuring and all that stuff. But before we do, I kind of want to give us one kind of more general conceptual, breakdown for matter before we start getting a little more mathy this lecture. I want to talk about ways to categorize matter. So matter you can split up all matter into two categories. Right? You have all matter. And it doesn't matter what you're looking at. If you have a sample of matter, it can be split into one of these two categories. You could have a pure substance, or you could have a mixture. And both of these are exactly what they sound like. A pure substance is all one thing. Everything in the sample is the same thing, whether it's pure water or pure gold or whatever. It's all identical. A mixture is a jumble of things, different things. All right? So pure substance, when we talk about pure substance, we're talking about all one thing. And when we talk about a mixture, we're talking about a sample of matter that contains more than one thing. Or I should say more than one type of thing. We can break these down into two further categories. You can have, under the category of pure substance, you can have what we call an element, which is all one type of atom. So an example of an element would be oxygen gas that we breathe, right, is O2. Copper metal is just a bunch of copper atoms strung together, right? That's an element. All the same type of atom. You can also have, for pure substances, though, you can have compounds. So you can have an element, you can have a compound. A compound is more than one type of atom. And now you may be going, well, wait a minute, wouldn't that be a mixture? And the answer is no. A mixture are different things mixed together in a big old jumble. A compound would be something like water, H2O. There's more than one type of atom present, so it's not an element. An element, all the atoms have to be the same. Water has hydrogen and oxygen both in it. But you can have a pure compound because you have just sample repeating units of H2O, just H2O, 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 all in the sample. And so they're all the same. They're all pure, but it's a compound because within that compound structure, there are different types of atoms. Hopefully that makes sense. Let me know if it doesn't. With mixtures, there are also more than one type of mixture. I'm actually going to scoot this over to give myself a little bit of breathing room. Whoa. There we go. So let's talk about mixtures. There are two types of mixtures. You can have what is known as a homogeneous mixture. You can have what is known as a heterogeneous mixture. A great example of a homogeneous mixture would be your morning cup of coffee. Because a homogeneous mixture is the same all the way through. It doesn't matter where it is, anywhere in the solution, you got the same amount of mixtures. And coffee is a great example of this. Well, part of it depends upon how much sugar you put in. If you put in a ton, then there's a sludge of sugar on the bottom of your cup. That's not a homogeneous mixture because it's not the same throughout. But when you add cream to coffee, you add the cream, you stir it up, your coffee turns all the same color, right? And that's because it's made a homogeneous mixture. It doesn't matter what region of coffee you're drinking from. There's the same amount of cream in each region. There's the same amount of coffee bean in each region. There's the same amount of water in each region. So like coffee is a homogeneous mixture. A heterogeneous mixture is a mixture where all of the parts of the mixture are not evenly distributed. All right, so in a heterogeneous mixture, a great example of this would be soil. Right? There's all sorts of things. There's rocks, there's dirt, there's mud, there's, minerals all jumbled up, and it's not the same. It's not evenly distributed. There's an uneven distribution of these different components all throughout the whole, so that is a mixture that is heterogeneous. It is not homogeneous. All right. So that's kind of our introduction to matter, some of the big general categories that we are going to be using and discussing as we move throughout the course of this semester. This first chapter really is a lot of, some of it may be review from a previous science course, but it's also very foundational. We're just kind of laying a broad general foundation for all the things that we're going to use moving forward. And what we're about to start discussing is might be the most important thing that we talk about in this chapter. We're about to start a conversation about units, followed by a conversation about significant figures. So let's start with units. So chemistry is a physical science, right? We're measuring things, we're observing things, we're taking down notes and measurements of substances, material that actually exist out in the world, out in the universe, right? And if we're going to be taking down data, recording data, taking measurements, we need units of measure, all right? We need units of measure if we're going to actually record meaningful data. If I told you that I set up a reaction in lab and the reaction was at 25 degrees, that statement is meaningless. It's meaningless because I haven't told you the units. And it makes a radical difference, the scale that I'm using. If I say 25 degrees Fahrenheit, that's sub-freezing. That's a reaction that is colder than the temperature water freezes. If I'm at 25 degrees Celsius, that's about room temperature. That's about 73 degrees Fahrenheit. So that's a huge difference. And the meaning of that statement, the reaction takes place at 25 degrees. The meaning all hinges on which units I was talking about. So everything, every number we use in this course needs to be accompanied by units, because without it, it's meaningless. All right? Units are incredibly important. Now, we live in America, and we have all grown up using the English system of measurement. The scientific community does not use the English system. We use what's called the metric system. And the metric system is the system that we're going to be using in this class. The metric system of units. All right. And in the metric system, length is measured with in meters. All right. The abbreviation for meters is M, a lowercase m. And just so you can know, 1 meter is 1.09 yards. So it's around 3 feet. 1 meter is close to 3 feet. We need a translation because we don't think in terms of the metric system, because we grew up here. We think in the English system. But meters, 1 meter is close to 3 feet. It's 1.9 yards. 1.09 yards, excuse me. Mass in the metric system is measured in grams, which is abbreviated with a lowercase g, and about 454 grams is 1 pound. All right, so a pound of weight is about 454 grams in terms of mass. So that should give you something. So we weigh tons, and not tons, but thousands of grams, right? Is the weight of a normal human. Volume in the metric system is measured in liters. And this is one thing where, for whatever reason, all of us here in America know what a liter is because we buy 2-liter bottles of soda. So we can think of a 2-liter bottle of soda, and then half of that's the volume of a liter. The abbreviation for a liter is a capital L. And 1 liter is 1.06 quarts. So that's an equivalent. But again, all of us are just picturing a bottle of soda and cutting it in half, and that's a liter. So that'll at least probably be the most intuitive. Now, here's the deal. Here's the reason why science goes with the metric system, and the reason why it just is more logical with the system of numbers that we use. Because the metric system is based on powers of 10. All right. In the English system, we have to create a different unit for different sizes. So for lengths, there's inches for little things, and feet for intermediate things, and yards for things that are slightly longer than feet. And then we jump from yards to miles. And those are the things we have to use. In the metric system, They don't have different units. All length is measured in meters, all mass is measured in grams, all volume is measured in liters, but they have a system of prefixes that they apply to these base units to change the scale. So if you're talking about a very heavy thing, you won't talk about grams, you'll talk about kilograms. If you have a very, very small volume, you won't talk about it in liters, you'll talk about it in milliliters. If you have a small, if you have a long distance, you'll do it in kilometers. If you have a short distance, you'll do it in centimeters. All of those things, those prefixes, centi, kilo, milli, change the scale of the unit. So these quantities here, these are what we call base units. These are base units that can be modified by adding a prefix in front of the unit, all right? And let's talk for a minute about prefixes. All right, and I'm gonna pause for 1 second. So prefixes, these are, if we were meeting in person in a classroom and I was giving you tests, I'd tell you you have to memorize them. You have to memorize them because these are just things that you got to know off the top of your head. I'd like to keep memorization to a minimum in my classes, but this is one of those things that there's just no getting around it. Now, we're not in a classroom, and I've already told you that exams are open book, open note, open all that stuff. So you don't have to memorize them, but you really want to be very familiar with them. Memorizing them would definitely help you take your test faster. But even if you don't want to memorize them, you should at least do this. I don't provide an equation sheet for these tests because you're taking them at home, you're taking them on your own, and it's open everything. But what I encourage you to do, all of you, I would recommend, I would encourage you, to make a custom equation sheet for taking your exams. All right, if you start now, you can add to it as we move through the semester. When we talk about something that's important or an equation that you might want to remember, you can add it to it, and that way you can have this thing as a reference while you're taking your test. And if you're not going to memorize these, have these prefixes on your equation sheet. That way you'll have them at the ready. If you don't have them memorized, you'll be able to quickly look it up and apply it and solve the problem. All right, infomercial over. Let's take a look at what these prefixes actually are. So we have first the prefix name, followed by the actual prefix, followed by the unit multiplier. All right, so these are, I'm not going to go over everyone. If you look up metric prefixes, there's a list as long as the internet. There's so many different units and prefixes. I'm going to highlight the ones that you'll be using in this course, the ones that I incorporate into problems that I write for your class. So these are the ones that will be relevant to this semester, but note that they're not the only ones out there. All right, so let's talk about prefixes. So the first one, we've already alluded to it, is kilo, right? Kilometer, kilogram, we've heard these. The prefix is a lowercase k, and the multiplier is 10 to the power of 3, or 1,000, right? So a kilogram is 1,000 grams. It's 10 to the third grams. The next, also probably going to ring a familiar bell, is centi. The prefix is a lowercase c, and this is 10 to the negative 2. So centimeters are tiny little meters. 10 to the negative 2. There we go. Next is milli. Those of you working in the health profession or nursing professions probably have heard of milliliters. The prefix is a lowercase m, and its multiplier is 10 to the negative third. The next is micro. Now, micro can't take m because milli already did. So what we did for micro, for the prefix, is we borrowed m from a different alphabet. We took the Greek letter mu. Kind of looks like a squiggly m with a tail. Micro is 10 to the negative 6. The last one that we're going to talk about here is nano. Nano has the prefix abbreviation of a lowercase n, and it is 10 to the negative 9. So these are the prefixes that I will be baking into problems, testing you on. These are the ones that you will have to use. Again, for the sake of speed, because time is going to be a constraint on the exam. You are going to be under time pressure taking all of these tests. I recommend memorization. But if you're not going to memorize them, then at least write these down on your exam sheet so that you'll have them at the ready, because you're going to need quick access to these things. One thing before we leave units. Can I explain why it's to the negative power? Yes. Absolutely. Ariana, because these... or I should say those prefixes make the unit smaller. So, for example, to illustrate this, if you took kilo, right? Hang on, new slide. 1 kilogram is equal to 10 to the third grams, all right? Or another way of saying this is 1 kilogram is 1,000 grams, because that's 10 to the third. Now, Robert, exactly. 1 centimeter is 10 to the negative second meters. You're like, what is 10 to the negative second? Well, 1 centimeter is, if you punch in 10 to the negative 2 in your calculator and hit enter, it'll say it's 0.01 meters. Now, that might be still hard to look at, but if you do some algebra, it becomes a little clearer. If you divide both sides by 0.01, they cancel on this side of the equation, and you'll realize that 100 centimeters are in 1 meter. So the negative powered prefixes are smaller than the base unit, the positive powered prefix larger than the base unit. And you'll notice on the previous slide that there's a lot more negative ones than positive ones, right? Oops. Negative power of 10, negative power of 10, negative power of 10, negative power of 10. But remember what class this is. We're dealing with chemistry. We're dealing with atoms, molecules, things that are very, very tiny. So the small units are far more relevant to us than the large ones. That's why we only have one in here that has a positive power of 10. Because every once in a while, kilograms shows up. So it's good to know that. All right. Okay. So we've talked about units. It's time to move on to the topic that costs students the most points on exam, second to none, in this class, in chemistry classes, at least in my chemistry classes. This is like saying, what is the number one most deadly animal in Africa? Ariana, you're so welcome. Right? What animal is responsible for the most human kills each year? I can't remember. It's like the hippopotamus or water buffalo. I can't remember which one of those scores higher, but far more than lions. All right. This is what I'm about to show you is the number one grade killer in this class. So if you're going to spend any time practicing anything I talk about today, make it this thing. We're going to talk about something called significant figures. Significant figures. They can be hard to understand. It's a way of thinking that's definitely challenging to get used to right at first. And it's probably the number one reason why students don't like me after taking my class. At this point, everybody more or less likes me because I'm, a chill dude. But this costs students a lot of points on tests if you don't put in the time to master them. So I'm begging you to put in the time to master them. If you do, then you have nothing to worry about. Something I want to say before we dive into what these things actually are is I want to give you just kind of a thing to keep in mind as you're working every problem. This is the paradigm. This is the mindset that you want. Every correct answer in this class has three components. All right. Every correct answer has three components. You have to have the correct value. Right? If the correct value is 10, putting 4 is an incorrect value, right? You got to have the correct value. Your number has to be correct. 2, you have to have the correct units. If the answer is 10 meters and you put 10 feet, that answer is wrong because it does not have the correct units. And third, you need the correct number of sig figs. All right. And this is what you want to keep in mind moving forward is you need all three. To get an answer right. So as we dive in and start talking about what are significant figures, how do you apply the rules, how do you use them, you need to have in your mind, this is vital, this is critical for me getting to me getting correct answers, all right? You've got to have all three of these things, the correct value, correct units, correct sig figs, all lined up if you get the answer correct. All right, with that being said, it's enough of a preamble. Let's dive in to what these things actually are. I'm going to kind of attack these in reverse order. First, we're going to talk about what digits are significant. So we're going to talk about identifying them. Second, we're going to talk about the rules for applying them. And then third, we're going to talk about why they're important. All right, why they make such why they're, well, significant, for lack of a better term. All right, so first, let's talk about identifying significant figures. So, and just to let you know, I'm probably going to say significant figures and significant digits. They're the same thing. Significant figures and significant digits are one and the same. So I'll probably switch it on that, and I just don't want you to be confused. So what digits in a number are significant? First, all non-zero digits are significant. All right, that's the first thing. First rule. Second rule. So that may leave you wondering, can zeros be significant? And the answer is sometimes they are, sometimes they aren't. Zeros are significant under two circumstances. The first is all zeros between significant digits are significant. All right, so all non-zero digits are significant. All digits, all zeros between significant digits are significant. And third, all zeros that are both, that's critical, there's two conditions here. All zeros that are both to the right of the decimal and right, so right of the decimal and at the end of the number are significant. You're like, that's a lot of words. I'm not even sure what any of this means. Don't stress. Let's break this down. Let's do some examples. All right. Let's actually apply these three rules for significant figures. What I would recommend, because I have to clear the board to write fresh stuff, is maybe open a second window for YouTube, scrub to this place in the stream and pause it so you can keep an eye on the rules for significant digits on one screen, and then we can work on the other. So you can kind of have a dual screen thing going on. All right. So let's do some examples. For each of these examples, yes, Carolina. Trailing zeros only when they are to the right of the decimal. And at the end of the number. And I'll do some examples. You'll see me kind of break all of these rules down as we go. So for all of these examples, I'm asking the same thing. Determine the number of sig figs in ... Let's take our first number. 325. Rule number 1 is all non-zero digits are significant. So we have in this number 1, 2, 3. We have 3 sig figs in 325. All right. How about 110? All right. The first thing you do whenever you're assessing how many significant digits are in a number, you automatically know that your non-zero digits are significant. So we have at least 2. Next, we have to determine, are these zeros significant? Well, if it's in between 2 significant digits, it is, and this 0 is not. If it's at the end of the number and to the right of the decimal, it's significant. This 0 is at the end of the number, but it's not to the right of the decimal. So it is not significant. 110 has 2 sig figs. All right. Let's do 101. Rule number 1. All of your non-zero digits are significant. All right. Now, is this 0 significant? Rule number 2 says all zeros between significant digits are significant, and this 0 is in between 2 significant digits, so it is. 101 has 3 significant figures. All right, let's do another one. Let's do 1001. All right, our non-zero digits are significant. Now our zeros here are in between 2 significant digits, which makes them significant. So the number 1001 has 4 significant figures in it because those zeros are between significant digits. All right, let's do another one. Let's do 3.00. Daisy, awesome job. Yes, it has 4 sig figs. Now, how many significant digits in 3.00? First, we have 1 non-zero digit, so there's 1. Next, any 0 that's between 2 significant digits will be significant. Well, I don't see any between any significant digits at this moment. Let's move to rule number 3. If a 0 is at the end of the number, we have one of those. This 0 is at the end of the number. And to the right of the decimal. This 0 is both at the end of the number and to the right of the decimal. It is also significant. So there's a second significant digit. Now, pop back to rule 2. Any 0 that's in between significant digits is also significant, which makes this 0 significant. So 3.00 has 3 significant figures in it. 3 significant figures in it. All right, now let's do, so let's go to our final form. Let's go to the black belt level. Let's determine the number of significant digits in 0.001900. All right. We're going to start with our non-zero digits because those are guaranteed. We have at least 2 significant digits in this number? Okay, Robert. I'll circle back around to your question once I finish this one. But I just want you to know that I see your question. I'll circle back around to it in just a minute. So first, non-zero digits are significant. I'm going to jump to rule number 3. It's a pretty useful one. It says that if a 0 is at the end of the number, we only have one of those, and it's to the right of the decimal, it's significant. This 0 is both at the end of the number and to the right of the decimal, so that 0 alone, rule number 3 makes significant. Next, any zeros in between significant digits are also significant. We only have one of those. So the number 0.001900 has a total of 4 significant figures. All right. The reason why I wanted to do this one is often students get confused by these dudes. Students get confused by these dudes because rule number 3, for whatever reason, the part that sticks in the head, and I remember feeling this when I was a student, the part that was always easy to remember was to the right of the decimal. But these guys, it's rule number 3 doesn't say to the right of the decimal. It says to the right of the decimal and at the end of the number. So remember, rule number 3 will only make one 0 significant if it is both to the right of the decimal and at the end of the number. These dudes right here are not significant. They're not significant. So that's, I would say, probably the most common kind of early mistake that I see. Yeah, totally. And it's super easy to make because we're just thinking, oh, if it's to the right of the decimal, it's fine. Remember, rule 3 says to the right of the decimal and at the end of the number. Rule 3 will only ever give you one significant digit. Then you might get a couple more if, like over here, we have someone who's in between significant digits. That'll maybe add some more, but it's got to be both to the right of the decimal and at the end of the number to be significant, or sandwiched in between. Yep. Okay, Christina. Not Christina. Christian. Exactly. Exactly. Rule 3 does not apply to that scenario. That's exactly it. Rule number 3 only applies if the last digit is a 0 and if the last digit is to the right of the decimal. You can do 1 and you can do 2. Oh, yes, we can totally do more. And actually, before I throw some more examples up here, I'm going to answer. Someone asked a question. Robert. Okay, Robert, let's take a look. Let's compare 11 and 110. If you look at these two numbers, they actually have the same number of significant digits. 11 has 2 non-zero digits, so it has 2 sig figs. 110 has 2 non-zero digits, but that 0 doesn't apply. Rule 3 doesn't apply because it's at the end of the number, but it's not to the right of the decimal. Rule 2 doesn't apply because it's not sandwiched in between. So both of these numbers only have 2 significant figures. That doesn't mean they have the same value. 110 is a much larger number than 11, but they have the same number of sig figs in them. Does that make sense? All right, let's do Okay, awesome, Robert. I'm glad to hear it. Let's do a weird one. Yes, yeah, yeah, and Robert, we will totally get to the real application. Right now, we're just seeing can we identify these things, and we're going to build complexity as we go. But if you are able to identify how many significant digits are in a number at this moment in time, that's all you need. That's all you need at this moment. All right, let's for our final act. Let's determine the number of significant digits in 1200.0100. First, we have our non-zero digits. We have 3 of them, so we are guaranteed at least 3. Next, and I always jump to rule 3 next, there is a 0 that is at the end of the number, and it's also to the right of the decimal, so it is also significant. Finally, all zeros that are in between significant digits will also be significant. So this 0 is in between 1 and our terminal 0, so that's significant. These 3 zeros are between 1 and 2. They're between significant digits, so they're also significant. So 1200.0100 has 8 significant figures. In this number, they're all significant because they're all sandwiched between significant digits, at least the zeros in the middle of the number. Yep, Robert, spot on, 8. Okay, now let's talk for a minute about where these things come from. All right, because we've been like talking about the number of significant digits. Oh, how many in this number? How many in this number? But it's so weird and it's so different than how we're used to thinking about numbers, right? Because like numbers are numbers. What do you mean significant? It feels like a made-up thing, especially if this is your first time kind of interacting with this idea. It feels totally made up. And once we start applying the rules, the mathematical rules for significant figures, it feels even more fake. So I want to talk about where significant digits come from. And the answer is they come from, measurements. They come from actually taking measurements of quantities. So let's say we have a ruler that I'm drawing out right here. And let's say we want to measure a piece of string. We want to see how long. And this scale is in centimeters. All right, so 0 centimeters, 1, 2, 3 centimeters. Let's say we want to measure a piece of thread that starts, we're starting it right at 0, and it's like this long. Let me ask you, how long is this thread? Well, it's in between 2 and 3 centimeters. It would be wrong to say that this is 2 centimeters long, right? Because we're holding it up to the ruler and we can see it's longer than 2 centimeters. It would also be wrong to say that this thing is 3 centimeters long because it's clearly shorter than 3 centimeters. But exactly how much longer than 2 it is, you can't really tell because there are no markings in between. So we have to just eyeball it and guess. All right, we have to take our best shot in the dark. And so you kind of look at it, you're like, well, let's see. What does that look like to you? It doesn't quite look like a half. To me, this looks like maybe 2.4 centimeters. Maybe it's 2.4. Here's the thing. If you said, nah, Josh, to me that looks like it's 2.5. Or maybe it looks like 2.3 to you. I can't tell you you're wrong. I can't, because there's no markings there. All right? This number, this last, well, first, this number has how many significant digits? 2. 2 significant figures in this number. And this last one, the last significant digit in a measured quantity is called the uncertain digit. The reason why it's called the uncertain digit is because it is 1 decimal place beyond the last marking on the ruler, and you don't really know what it is because the marking's in it. So if you made this measurement with this ruler, you would get a measurement that has 2 significant digits in it. Because that's the best we can do. Let's compare this measurement with this ruler to a measurement taken with a different ruler. A ruler that I'm going to draw in green. A ruler that has a greater precision. So 1 centimeter, 2 centimeters, 3 centimeters. But on this ruler, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 markings in between each centimeter. Let's measure the length of this string now. All right, if we do, let's go dot, 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 dot. Boom. Where is this? 1, 2, 3, 4 spaces in. If we take this measurement with this ruler, yes, Carolina, exactly. Oops. Carolina, that is exactly correct. For the first ruler, 2.3, 2.4, 2.5 are all correct because that last digit is uncertain. All right? Let's write down what the measurement would be. Yep, that would receive full credit. Absolutely. It absolutely would. Let's talk about what the measurement recording would be if we did it with this green ruler. Well, now, if you look at this, we would say that, okay, this is definitely 2.4 2.4, and maybe to my eyeball, the way it's lining up, I'm like, well, it looks like it's just a little bit past 2.4. So I'm going to call it 2.41 centimeters. And maybe you're going, Josh, that doesn't look like 2.41 to me. That looks like it's right on, exactly on 2.4. I'm going to call this exactly 2.4. And guess what? You can, as long as you call it 2.40. Both of those recordings are fine because that last digit, that last significant digit is the uncertain digit. The last recorded digit in any measured quantity is uncertain. So if it looks like 2.41 to me and it looks like 2.40 to you, that's fine. We don't have explicit markings telling us whether it's spot on, just a little bit above, just exactly there, because there's no markings there. That last one is uncertain. And you'll notice that the measurements taken with the green ruler have 3 significant figures. Robert, exactly. That is an excellent way to state it. It makes your measurement, or I should say, having a more precise ruler, like we have here, more precision, more precise markings, it reduces the error in your measurement. In the first one, we had plenty of room for error because we were eyeballing it. We're like, it looks approximately, but we have no way to really judge. But having a more precise instrument measuring device reduces that error because the amount that you're guessing now is a smaller quantity. All right, so the big take-home message here is, and this is kind of the answer to the why. All right, why are we even doing this? Significant figures, or I should say, the number of significant figures is determined or I should no, I'm gonna restate this again. There's a better way to say it. The number of significant figures reflects the precision of the original measurement. All right, the number of significant figures reflect the precision of the original measurement. And so the reason why they matter is the more significant digits you have in a number, that means that that measurement that was originally taken, that was originally collected, was taken with a device that was more and more precise. And so as we learn how to include significant figures in our calculations and apply them there, the reason why we're doing it is because it all stems back to the device, the measuring tool that was used to take that data in the first place. So it's preserving the precision of that original measurement through the calculation as we do it. So that's the reason why we're doing it. It wasn't just made up by chemists who wanted to ruin math for the rest of you. Okay, so that's kind of the big picture. That's why it's so important. And so anyways, that's kind of where they come from. Now that we know how to identify how many sig figs are in a number and where they come from, let's quickly talk about the rules. All right, and I'm gonna say up front that we may not finish this part, but if whatever we don't, we'll pick up our next lecture. So let's talk about adding and subtracting with sig figs. Actually, well, yeah. Well, let's do this one first. So when you're adding and subtracting numbers is the precision of your answer must be the same as the least precise number that was added or subtracted. All right. Now, understanding this definition hinges on understanding what precision is. All right. And precision the precision of a number is determined by the last significant digit in the number. All right, precision is determined by the last significant digit, and it's determined like this. The further to the right that last significant digit is, the more precise. All right, we could see this in the two measurements that we were looking at on our previous page. One of them was 2.4 centimeters. The other one was 2.41 centimeters. When you look at the last significant digit in each number, this one is in the tenths. Oops. For 2.41, the last significant digit is in the hundredths. Right? Because this one is further to the right, it's more precise. All right? Because it's further to the right, it's more precise. So that's precision. When you add or subtract two numbers, the precision of your answer must equal the precision of the least precise number you use. So, for example, if you were to add the numbers 31 centimeters plus 40 centimeters, if you punch this into your calculator will tell you the answer is 71. Now remember, the correct answer, every correct answer in this class has three components: value, units, sig figs. The correct value is 71. That's the correct value. Correct units, centimeters. Now let's look at sig figs. 40 is precise to the tens place. 31 is precise to the ones place. Our answer must have the same precision as the least precise number we added, which is 40. That means that our answer must have its last significant digit in the tens place, and 71 does not. 1 is a significant digit. So we need to round, and 1 rounds down. So the correct answer is 70 centimeters, because 70 has its last significant digit in the tens place. Let's do another example. Yep, Carolina, spot on. Let's do 2.41 kilograms minus 0.68 kilograms. All right. You punch this into your calculator, which is what I'm doing right now. 2.41 minus 0.68 comes out to, so the correct value is 1.73. We need correct units, kilograms. Now we have to look at our sig figs. 2.41 has its last significant digit in the hundredths place. 0.68 also has its last significant digit in the hundredths place. And 1.73 also has its last significant digit in the hundredths place, so we do not need to round or anything. 1.73 kilograms is the correct answer, because the precision reflects the least precise number added and subtracted. In this case, it's a tie. All right, sorry. Brianna. I am okay, and Rox, I'm just seeing your question on the previous one. So first off, Brianna, what determines your last significant digit? So when you're adding or subtracting, you're focused on the precision. All right, you're looking at what is the last significant digit in this number, and your last significant digit, your precision of your answer has to have the same precision as your least precise number, because 40 is less precise because 40 is less precise than 31, the answer must have its last significant digit in the same place. Its last significant digit must have the same place value as 40. 40's last significant digit was in the tens place, so our answer must have its last significant digit also in the tens place. And yes, Robert, we are rounding down because 1 doesn't round up. We're not going to round 71 up to 80. We're going to round 71 down to 70. All right. Again, Rox. Yes, 1.73 does have 3 significant digits. That is 100% correct. But that's not the reason why it's the answer. The reason why it's the answer is because you have to have the same precision as, okay, awesome, awesome. It has to have the same precision as the least precise number that we're using. So we have to be precise to the ones or hundredths place here. Totally. All right. How are we doing on time? Okay. That is so it is 6:36. We will do more examples on we are going to do more examples on whoa, why is that all funky? We'll do more examples on today's Thursday. I almost said Monday. We won't do them on Monday. We'll do more examples on Tuesday with addition and subtraction. We'll also learn the rules for multiplication and division, and then bring them both together. Dude, sig figs are not easy. Daisy, that is correct. So yeah, so here's the thing. You've gotten your first taste. Significant digits are not easy to handle. This is why they cause the greatest amount of points loss on exams. Like, it doesn't matter what class. Like this, whether it's Gen Chem, it doesn't matter what topic. This one always trips students up the most because it affects all the math we do in this class. So the one way to get around it is to practice, practice, practice. You want to do as many of these types of examples as possible so it becomes second nature, like breathing. That's my biggest recommendation. So this weekend, hit sig figs hard. I would even recommend checking out the sig figs lecture that I did for Chem 305, or even my Chem 400 sig figs lecture. Give those a shot. See if you can learn the rules for multiplication and division so that when we roll in on Tuesday to lecture, you already know what's up and you can do the problems live as I'm doing them, and they're maybe not as confusing. Anyways, that's my study tip for the weekend. I have a lab in about 10 minutes with the Thursday people, section 62. Yeah, totally, Christian. We're gonna we have like, I think it doesn't start up till like 6:45. It might be a few minutes later because we're running a few minutes over here. So we usually break for 10 minutes, and then we'll be back. Lab is nothing formal this week. The people who hung out last week saw. I'm gonna maybe talk for 10 minutes, and then I'll still be here. You can ask me questions, but you're free to bounce afterwards. There's no pre-lab for this one. There's no in-lab assignment. Totally. All right, so I'm gonna bounce. Let's stretch our legs, use the restroom, get a snack, kind of shake the cobwebs, and we'll be back in about 10.